Hello, this is Fran Diamond. I work at the Center for Forensic Science Research and Education, and what we're going to talk about today is a very interesting new product from Waters called the RADIAN ASAP. It is could be described as a rapid drug detection system. So we had a collaboration with Waters to test out their system, and so although this is still preliminary in nature, I did want to share some of the results that we had with you. So just to outline kind of the flow of this talk, we're going to talk about forensic chemistry because this instrument, this is a very exciting instrument that may fill a role in forensic chemistry testing. So we're going to talk about how that would fill that role. When we talk about the instrument, we're just going to talk a little bit about just the theory of operation, what is going on inside the instrument, the mode of operation, how does someone sit in front of it and run this. We're going to generate some data, so we're going to look at, what does that data look like, and the utility of the data. How is this going to be data that is of value in the forensic chemistry community? And then after that, we're going to talk about our specific project with the collaboration with Waters, and we actually involved NMS Labs to provide us with some authentic samples from some seized, from some drug seizures that we got in casework. So these are discarded autosampler vials, and so we'll just talk about the findings. We'll discuss some of the advantages and some of the disadvantages of the RADIAN ASAP system, and then talk about future considerations and just kind of wrap that up with a conclusion. So, as I said, our assessment was really to determine how well this is going to work with seized drug analysis. And a seized drug analysis, is basically can be as easy as you have a white powder that could be cocaine. You could have a brown mixture that could be any number of different compounds. You never know what you're going to get in forensic chemistry. So what we wanted to do is just determine, would this be applicable to do some of that preliminary testing that drug testing laboratories do? A traditional test includes some rudimentary color tests. Some people might run a quick FTIR scan to get a feel for, what could the compound be? At the end of the day, we want to have two pieces of information that are independent of each other that kind of confirm of what we're looking for. So what we wanted to do is to see if this RADIAN could fill that role of just providing upfront data that is going to direct a forensic chemistry on what might be, the next line of testing. So in order to fill that role, it has to be easy. So our evaluation was including ease of use. How easy is it for a forensic chemist to just sit in front of an instrument and generate this data? And then secondly, the quality of the data has to be stand up to the scrutiny of court, okay? And it also has to be explainable by a forensic chemist. So, so the RADIAN system itself is actually a direct probe mass spectrometer. Okay, so we have the ability to apply our sample to a glass capillary and put that directly into the mass spectrometer to generate data in seconds instead of minutes. Okay, there's no chromatography. It's really just inserting, ionizing, and then reading our data. And I'll explain what the data look like. So SWIG drug, for us in the United States, defines the quality of various testing schemes, category A being the highest. And so mass spectrometry is down here as a category A. There are other category A's here too. Category B includes techniques, non-mass spectral techniques like gas chromatography, liquid chromatography, TLC, UV vis, and then their color C. So these are kind of the least discriminatory tests that are done, and this includes color tests. So these are the tests that are the category C may be the upfront tests that are done to determine what the material is. But category A really provides much more detailed information. So as far as identification criteria, SWIG drug recommends that we have at least one category A technique, and then we can follow that up with some other techniques. And that's why color tests are performed, so that we can get that non-category A test and then confirm that by something like, typically, GCMS is pretty much the workhorse of forensic chemistry laboratories. So I'm not going to explain each one of these color tests, but over the years there have been a large number of different color tests that some very smart chemists have come up with to run to kind of determine upfront, what kind of drug do we have. Cobalt thiocyanate is probably one of the most popular. It turns blue when you have a positive cocaine. Now, that said, that doesn't mean it's absolutely cocaine. There are other things that are going to give a blue color, and that holds true for all of these different color tests. But I just wanted to display over the years, people have used these color tests as a means of doing this upfront confirmation. Now, that takes time, that takes experience, it takes a certain amount of money preparing these reagents. So color tests, while not using expensive instrumentation, it does take time and resources to run. So, I'm sorry. This is the RADIAN ASAP system. All right, so it's a very small, piece of equipment here. Very small footprint, doesn't take up much space on the lab bench. Doesn't require high voltage. What it does require is nitrogen to come in, and there's very little waste that is generated because we don't have effluent from an LC coming in here. So there's very little waste that is generated. So as you can see, it's a very compact unit, ready to go. Just open the door. This is where, so it's suitable for a wide range of samples, and basically because we don't have to worry about a dirty injection port or fouling a column, we can basically put our samples directly into the mass spectrometer. Okay, so the workflow is simple. Dissolve your seized drug in a suitable solvent. It could be in water, it could be in methanol, and you're just going to dry off a capillary and insert it directly into the mass spectrometer, and you're going to start acquiring data right away, and you're going to get a mass spec data in less than a minute. Okay, and the quality of the mass spec data is really determined by processing by the live ID software. Okay, so just to show you here the system, you have a glass capillary. You clean that. You can apply your sample to that capillary and then insert that directly into the mass spectrometer and hit start. Live ID is going to analyze that data as it comes off in somewhat of a unique fashion. So I'm going to show that in the upcoming slides. So what happens when we insert this directly into the source? Okay, so you can see the capillary directly in there. We have a source of hot nitrogen gas coming off, and we have a corona discharge pin in there. So this is very similar to APCI in terms of ionization. And the nitrogen serves to create this corona discharge that is actually going to end up ionizing our sample. So people that are familiar with LCMS know that in APCI, under the right conditions, ionization is performed, but we don't get much fragmentation. And that's what we're going to utilize here. So initially we get protonation of our control substance, and then we can control what kind of fragmentation happens next. And here is where we have that fragmentation. If we look on the right-hand side, starting from the bottom to the top, CV being cone voltage, right? So the cone voltage actually promotes additional fragmentation in the ion source by accelerating our charged particles and causing additional collisions and breakdowns. So at a very low cone voltage, we tend to get very little fragmentation. And as we move that up to a cone voltage of 25 and 35 and 50, you can see we get subsequently more and more fragmentation. And that's what we're doing in the system when we do this acquisition. As soon as we hit start, it's going to run through acquiring at these 4 different cone voltages. And what we can do is basically we get 4 different mass spectra for everything that is added onto the column. Sorry, there is no column. Okay, so in the end, here's what we get. Live ID will examine those 4 traces and compare that to a database where the same process has been performed on analytical standards, and you get a match factor, a quality fit number. In this case, we have codeine at 98%. We also have a hit for hydrocodone, and those of you who are familiar with this, you know that these 2 compounds are isomers of each other. They have very similar mass spectra. So it showed the hydrocodone probably as just a secondary hit, unless there's a trace of hydrocodone in the sample. The one thing you're not going to get with this system is you're not going to get chromatographic separation. All right, so this is how our data looks. Don't be fooled. We're not looking at a peak. This is just showing how ions are formed inside the source, and this is just a trace of everything that's positive. So this is actually an example of street heroin. Okay, so and as you can see on the right-hand side, we have compound and match score. We have fentanyl, a very high probability of fentanyl in here. We have diamorphine. This is actually probably heroin or heroin breakdown, and then 6-monoacetylmorphine. So this is typical of what we see in street heroin. So this is a good application in that you can see it identified 3 different forms without chromatography. And that's what Live ID does. It pulls out data from those 4 different voltages, and the algorithm in there searches each one of them to determine if there's one or multiple components in your sample. So here's an example where we get a tablet submitted for testing. Looks like Flualprazolam or Xanax. Okay, so when we run Live ID, we find out actually it's Flualprazolam. Okay, so this is one of these counterfeit compounds, counterfeit formulation containing one of these new, we call them novel psychoactive substances. So this is just an example of how live ID and the RADIAN system is going to help identify something up front. Again, what we have here is we have the 4 different cone voltages of our sample on top and the library entry on the bottom. And what live ID does is looks at those 4 traces to determine what is present. You can see here, we have a very good match actually at the 4 different voltages. So basically the mode of operation is we took some extracted samples from NMS labs, and these were random samples. We just said, give us, 100 or 200 samples, and we'll start to work with them. So we just took them, we evaporated the extracts that they supplied, we took them down to dryness, and we reconstituted them in 50 microliters of acetonitrile. We rinse off the glass rod with methanol. We allow that methanol to dry, which is almost instantaneous. And then we're just going to submerge the tip of the glass capillary into that sample solution. We pull it out, let it air dry. Again, that happens quite rapidly. And we load the glass rod into a small little canister. It just clips right in. And when we insert it in the instrument, we can either choose to start the acquisition, or we can start an acquisition for multiple samples. And we can discuss that briefly. So before we start, of course, we want to clean that glass rod before and after. We want to demonstrate that we have a clean background. Anyone who's familiar with forensic chemistry knows that a good lawyer can ask for, is it contamination from a previous sample? So, the glass rod, we want to run that as a blank injection just to show that there are no drugs. And we may want to do this before and after each sample just to ensure that we don't have this carryover. If we do have carryover, we may have to run a blank acquisition, numerous times. As it turns out, Waters has developed a bake-out program that is actually designed to clean out that chamber between each acquisition. So, that in our case, we were running multiple blanks between samples. With the bake-out, that may not be necessary. So what we did is just to make sure that we understood how the system worked. We ran just neat standards. We had 0.1 milligram per mil solutions, and we applied them onto the capillary, put them in, and we just searched it out to see if our neat standards were identified. And if it was in the database, they were identified. We also have a standard test mix where we have 8 compounds, and we introduced that into the system, and the RADIAN ASAP system found 6 out of the 8 compounds in the test mix. And 2 of those compounds, methamphetamine and phentermine, are isomers. So we wouldn't expect that both of them would have been identified as individual components. And then as we ran our samples, the ASAP system was able to detect common controlled substances. And in addition to that, some of the adulterants, again, as long as they're in the library, it's going to find them. And so here's just an outline of the comparison with testing with NMS labs. And again, these were random exhibits that were sent up for testing. And you can see for samples of interest found by GCMS, we had found fentanyl in these. In 39 out of 40 of them, we also found it on the RADIAN system. THC, a little bit more problematic. THC we're not quite sure what all the issues are with THC. We spent a little bit of time on this, but we haven't completely resolved this yet. As far as methamphetamine, 22 were found by GCMS, 19 on the RADIAN. Buprenorphine, 8 out of 8. Cocaine, 7 out of 8. Now, for a number of these exhibits, the secondary hits, like THC, were present at much lower levels. Okay, so the one thing that you don't get on the RADIAN system is the relative concentration of these various compounds. So we also had numerous negatives, and we had to verify that the ASAP system also determined that these were negative. We didn't know what graphic to put up here for negative samples, so we just put a statement up that 59 samples were negative on both systems. So what are the challenges of sample analysis? Mixtures. Mixtures are going to be problematic because we don't know what the relative amounts of different components are in these mixtures. What we have found is that the primary component seems to be the one that is identified faithfully with the ASAP system. We are working with Waters on problems with some multi-component mixtures. We did some testing on the system, and I know that Waters is working on improving this aspect. Trace analysis. So if you get a sample in and you run it and you get a negative, does that mean it's negative, or does it mean you have to concentrate your sample? And that really comes down to a laboratory protocol. So you may or may not have to concentrate your samples. Another thing, that because this is positive ion mode, we're not going to see acidic compounds. Acidic compounds, of course, they don't ionize in positive ion mode. So compounds, classes like barbiturates, NSAIDs, they're not going to show up. A problem that we saw is signal saturation. Again, you're inserting a certain amount of material directly into a mass spectrometer, a very sensitive mass spectrometer, and your signal at times can get very high. For those of you who can read the left-hand margin for the y-axis, we're in the tens, if not hundreds of millions of counts here. And we do get a indication that we have signal saturation. So the system determined that some of the signal was saturated, and that's good. And so it reports that back to us just to let us know, hey, your most prominent components here are a little bit saturated. You may want to run less to get a better quality match. So the advantages of this system. First of all, I'm going to tell you, on day one, we just looked at each other, the two of us working on this, and said, this is awesome. Because you get a result within 1 minute of high specificity, because it's mass spectrometry and it has select ionization at these 4 discrete ionizations. So we have the ability to identify drugs in mixtures without prior chromatographic separation. Now, the mixtures is going to be problematic because all the different mixtures, especially if something's present at trace concentrations, are going to challenge the system. But there's little to no sample preparation. Literally put a couple milligrams in a milliliter of solvent, and you put the capillary into that and introduce that into the mass spectrometer. So sample preparation is very similar to color tests. None. It's really just aliquoting small amounts. So what does this do? It reduces user intervention. Okay, that's a good thing. Okay, so you don't have to be a professional at mass spectrometry to generate data. And that's not to say that we're looking to put dummies in front of it, but we want to be able to have a system that is a walk-up system where you can readily generate data in a short period of time. And because of the nature of the data, you can reduce some of the subjectivity and decisions and bias that come from running color tests. So this is a faster screening method when you compare to color tests. And thin layer, you're not waiting for anything. You're not putting a sequence on. You're not doing all of those things that by their nature take time. And this variable cone voltage is very good in terms of it's a much added benefit to be able to see specific fragmentation at these different cone voltages. It's easy, minimal training is required. So I'm involved in teaching an instrumental course for forensic scientists. We had the system in-house, so part of our mass spec lesson is I had them, the students, run their unknowns. They were given unknowns and they ran it on the system. So they had minimal training. We just told them, here's what you can do, here's what you can't do. And they ran their samples and they got their results. So because your data acquisition is mass links, you can actually go back into the data and do more interactive analyses. We did this because we were wondering why we weren't able to find traces of compound A when compound B was present. And we went into mass links and we could see, okay, well, it's there, but its intensity is much smaller than the major component. So if you're comfortable with mass links, you do have the capability of going further than live ID. Okay, so some of the disadvantages are going to be, if you're used to chromatography, if you like that separation, you're not going to get it with a system like this. So as such, because we can't separate compounds out, we're not going to be able to identify all the components in a single sample. Because we don't always know what's in a sample, sometimes we get carryover. So the lab is going to have to develop carryover strategies. When we were first learning, like I said, THC, caffeine, these tended to generate the most carryover. And as a result of what our strategy was just to run blanks over and over again. Waters has this fake-out procedure for proceeding with this. We did have some trouble with heroin matching to live ID. We did actually work with Waters on this, and they have made progress on being able to identify heroin in mixtures. This could be seen as a disadvantage, is that we have limited user intervention. The analyst can't change any parameter except cone voltage. Well, you may want that because for established methods in a forensic chemistry laboratory, we don't want to customize everything. It takes time. It takes folks having the know-how to do that. So the idea is that you walk up to the instrument and generate data. That could be a disadvantage or an advantage. Sequencing can be problematic here because you don't know what the carryover is going to be. So the way we ran the system is we sat in front of it, made acquisitions, reviewed the data, and made a decision whether to go next. So sequencing doesn't work in the traditional sense where someone sits down in front of an instrument, types in 30 samples, and walks away. So some of the future considerations after working with Waters, more library additions is going to help us. For those samples that contained components that were in the library, they were identified. But we need to add a number of compounds to this database. At some point, I think it would be good to have more interaction with the live ID software. It works great. We don't understand the algorithm, but the results are very good. And then, we want to try to test more challenging samples just to see, can the system handle this? And, can we process more complex mixtures? And these are just strategies, future considerations that we have for the system. So in conclusion, the RADIAN is very robust. It is, again, you sit down, you insert the capillary and hit start. And you are able, Live ID generates the data automatically. The sample preparation, very simple because you're just diluting. Results, very rapid in a minute, okay? So it's very amenable to labs lacking advanced mass spectrometry knowledge and skills, okay? We don't have that in every laboratory. Forensic chemistry laboratories, they're very good at GCMS, but, may not understand, the complex nature of this testing. So it's very amenable to labs that do this type of work. So with that, I'm finished my presentation, and I will be willing to take some questions.